So Paul and Ben will be leading a debate on the pros and cons of machine learning to insurers and society. And that's all I'm going to say. I'm going to hand it over to Ben and Paul. Feel free to introduce yourself, just in case anyone doesn't know who you two are.
Yeah, so I'll kick off, and then we'll move on to Paul. So I'm Ben Smith. I work in risk analytics. So we're a team in the actuarial department at Aviva, but we use machine learning and things to look at customer problems as well as actuarial problems. So we're not just focused on the traditional actuarial areas. Before we begin, I will just say, Paul and I have taken polar opposite views on a complex and nuanced debate. They are not necessarily our views. We've taken them to aid the presentation and to be deliberately provocative. What we hope will happen is that we'll get lots of feedback and debate, and we'll leave plenty of time at the end for us to have a discussion of these themes. They're not necessarily aimed at insurers, but they are a useful debate to have, given that we are increasingly using these kind of things to do various different tasks within our day jobs. With that, I'm happy to hand over to Paul. I will be presenting the case for machine learning and AI. Paul will be presenting against machine learning and AI.
Thanks, Ben, and hi everyone. My name's Paul Moorshead. If you don't know me, I've been an actuary for over 25 years now, mostly as a consultant, and then working with many of you here for the last 7 or so years. I've completed various Python and machine learning courses, and I'm steadily incorporating data science into my day job as head of reserving here. Today I'm going to be the Luddite, explaining the headline challenges around the application of machine learning. For those of you who don't know, Luddites were people who fought back against the onset of the Industrial Revolution by smashing up new technology. It's not quite what I have in mind for machine learning, but I do think there are a lot of considerations that have been ignored in the rush to adopt what is an amazingly powerful and freely accessible technology. One only has to look at the internet or pick up a newspaper to see the huge value being created by machine learning right now. We can see how valuable machine learning companies such as Facebook and Google are. We know how much our daily lives are influenced by algorithms, both positively and negatively. For instance, when I first logged on to Netflix, I was being recommended programs that the average customer of Netflix liked, but which really weren't for me. But after only a few likes and watching a few programs, a host of suitable programming opened up to me, and I'm still trying to get my way through that, as most of you probably are. We all read about how highly rated machine learning jobs are in job seeker surveys right now, even higher than actuaries these days, it seems. If you look on enviously at how highly paid machine learning jobs are right now, that doesn't mean we shouldn't reflect on what we and these models are doing, quite often in the background and out of sight, and think about how we can do the right thing for ourselves, for our customers, and for our companies, as well as for society more broadly. As Ben says, these aren't necessarily our views, but I do think these points raised here on both sides are important for us to discuss, and I really encourage you to send in your comments and questions so we can have a great debate today. So my first headline is that machine learning models are black boxes. Let me explain why I say that. Let's take random forest models as an example. A random forest model is formed of many, many decision tree models. And decision tree models themselves are nice and simple. You start at the top, and then at each node you go left or right, depending on some characteristic, until you end up at a homogeneous endpoint with a defined output. In this exhibit here, if this was a motor insurance model, then you might split at the top, looking at previous claims history. Then you might look at vehicle value, then driving experience, and then policy holder location to get to a premium of, say, £500. Nice and simple, easy to follow. But the only problem being that these nice simple models just aren't very predictive. So what people do instead is get a machine to soup it up by applying a random forest model. The computer takes random chunks of our training data through decision trees over and over again, 100 times as the default in Python, and then averages the outputs. The results, the outputs, get much more predictive, but then deciphering the logic behind it all gets so much harder. For example, I built a random forest model a couple of years back to predict how long my newborn son would sleep at night. It fitted like a dream with only a few weeks of data. I excitedly told my wife that my model was accurate to within 10% of my son's actual sleep time. So she naturally replied, "Okay, what do we do tonight then to maximize his sleep?" and I had to sheepishly tell her that I didn't know, as the model only told me what would happen based on known input factors, time to sleep, fed well, etc., and not which of these factors was important to a good night's sleep. On an aside, this is a great example of why you need to fully understand the needs of your stakeholders before building a model. As a new mum, advice was the value add she wanted, not a whizzy model and pretty graphs. If I compare this to classical regression, GLMs, these give a very clear explanation of the logic. Essentially, y equals mx plus c with some actuarial bells and whistles. But that's not the case with random forests, and the consequences of this will be discussed more later. Let's now look at another popular tool, neural networks, where the logic is at first sight more easily available, but is actually almost impossible to follow in practice, even for someone as clever as Sherlock Holmes. To explain how it works, a neural network takes a series of input values, the blue blobs here, applies operations, be they mathematical, Boolean or otherwise, to combine and transform all those input values into a hidden layer of new variables, the white blobs. And it's these white blobs which are then used to actually calculate the output value, the orange blob of the neural network. In more complicated neural network models, there are additional hidden layers of new variables, which are themselves formed by combining and transforming the previous hidden layer of new variables. So very quickly you go from the comprehensible, understandable blue input data to incomprehensible gobbledygook white blobs on which the model actually runs. One of the tasks I completed on the Andrew Ng machine learning course was to build a neural network to recognize handwritten characters. It was scarily easy to do, as well as being very predictive. But I was fascinated to see how the neural network was looking for patterns in the hidden layer that, when I looked at it, just seemed like grey goo, not at all how I think my brain works when I'm deciding if someone with bad handwriting, like myself, has written a C or an E, for example. It didn't seem to be looking for a straight horizontal line in the middle to detect an E, for example. As with random forests, neural network models are highly predictive and extensively used. However, the effect on the results of the understandable input data is lost, and we're left with a black box doing things we cannot possibly understand. Again, the consequences of this will be discussed later.
My retort to that would be, traditionally we've focused on how something gets to an answer and not necessarily why. We're very used to being able to track an equation on a piece of paper or through a piece of code from one end to the other, and then find it hard to understand what's happened given that thought process. Actually, machine learning gives you a really good methodology to understand why the model is saying what it is. If you're willing to walk past that, you can't necessarily follow through how each and every complex interaction takes place. So, for example, it gives you a brilliant method by which you can explain and find the most parsimonious complexity in your model, i.e. how many terms should I add to a given model before it starts becoming less predictive, and it gives a robust way of doing that. That's actually one of the things we found harder traditionally when we were adding terms. There was always weird and wonderful techniques to stop us adding terms, after which it became no longer predictive, but we were simply just solving for noise in our models. There's also various other ways that you can see exactly why the model is saying what it is. It'll give you trends. You can understand in individual partial dependencies what it thinks is happening. And there are also various methods to rank the order in which it thinks those factors are most important, albeit there will always be collinearities. The other thing I would say is GLMs are always quite an art form anyway. There was lots of things that the layman would have struggled to understand that went on under the bonnet in a lot of GLIMs to make them fit well. So there was whole books dedicated to them in themselves, whole university courses. So I'd argue what we're moving from isn't necessarily that simple either. The other point I would add is, if we can go to the next slide, Paul, is that actually there's a lot of value in that stuff that we can't otherwise follow through. We are limited in what we can do, at least in the way that we've been traditionally taught. Part of the real value for this stuff is it can spot things that we can't necessarily spot ourselves or solve for ourselves explicitly. And that's where a lot of this value is. And there has been multiple use cases as shown on the screen where AI is now either at or outperforming human levels for specific, albeit narrow tasks.
So I'm going to start this slide with a definition. Machine learning is the application of artificial intelligence that provides systems the ability to automatically learn and improve from experience. I found that definition on the internet, and I can understand how that can make machine learning sound so appealing to data scientists, CEOs, and investors. Keep throwing enough data in the direction of the model, be that data real, simulated, bootstrapped, inverted, fuzz, defuzz, whatever, and in the end your model will solve all. A great example of this in practice would be teaching a computer to play backgammon, define the rules and then just let it play itself thousands and thousands of times while it learns all the best positions and gets stronger and stronger. The problem is that real life problems are just so much more complex and harder to solve than self-contained games like backgammon. There can be so many possible situations that rare or unseen events just don't come up in the training data. And so the model doesn't know how to react and can make errors. The Uber self-driving car fatality being one tragic example of what can go wrong in practice when such rare events occur. It is interesting to note that Uber has since sold their self-driving car unit, but don't feel too sorry for them. They did make $10 billion in the process. Furthermore, research has shown that rain, fog, and snow have a huge impact on the ability of machine learning algorithms to identify images. If a self-driving car can't identify an image, it will be self-driving blind. And as all these issues are hidden away in these complex models, we don't even know what the weak points are in those models, and so we can't easily address or mitigate them. And before you get into a self-driving car in the UK, should you consider that the models driving that car were calibrated in the perfect Californian sunshine and not the grey skies of London? Check out the weather and vegetation next time you see a video of a well-behaved self-driving vehicle, and then ask yourself how many palm trees you see when you go out driving. I appreciate not everyone is using machine learning to build self-driving cars, but the principle remains. You may build a perfect model for one purpose or set of customers, but do the users of your model know the limitations of its use? Or are they blindly applying it to another totally different purpose or customer base as well? Or even worse, are they applying it only to a new purpose or customer base with no knowledge of how the model will react in this new environment?
In response, my argument would be, yes, models are imperfect. Yes, they get things wrong occasionally. However, couldn't you argue that against any process model machine or anyone in society for that matter, without becoming too political or topical? Humans haven't made brilliant decisions over the last period, and that's mainly due to lack of experience or training under the circumstances they're being asked to make decisions. We could equivalently say that's exactly the same for these machine learning models, to use your point, Paul. If you were to feed in data from the UK, could that not be equally well used to optimize your models and make them that bit safer? Generally speaking, when the computers get things wrong, it's not necessarily the computer that has got it wrong or the algorithm. It could generally be boiled down to whether the person training that model has done the right thing or appropriately called out the limitations of that modeling and when and where to use it. It's the same old actuarial trope. If we can move on a slide. Great. Which leads me on to my main point. It's not necessarily the government, the algorithm that's wrong. It's that there's usually has to be some level of governance that sits around it. The data scientist should have as a responsibility the ability and the tools available to communicate the model limitations and their implications to make sure the people who are making decisions on those models are using them or consuming them know exactly what they're doing. The other point I would make is humans aren't perfect either. Whilst it's sad and there will be less than optimal outcomes by machine learning algorithms, you also get that with human behavior as well. Sometimes it may be found that the models might outperform the humans.
Machine learning requires data to analyse, but for many purposes, there is actually too much data. Having just raised the issue of self-driving car models not having enough data, I'm now going to explain why self-driving car models are also an example of where there can be too much data where data is available. The reason is that these models need to analyse huge numbers of photos. If each photo has, say, 1,000 by 1,000 pixels, that's 1 million data points per photo, each with an almost infinite number of colour values. To fix this, often the solution taken is to reduce the resolution and make the images grayscale. Say make each image 100 by 100 pixels instead of 1,000 by 1,000, leading to just 1% of the original data points. Now, I am aware that there's an approach called convoluted neural networks, which can do this in a clever way to minimize the loss of information, but you're still losing a portion of your valuable data. So, having thrown away a lot of data, you can get your model to fit, but at what cost? Imagine driving with your eyes squinted all the time. Look at the image on screen. I don't even know if the vehicle is on the correct side of the road. And is that a traffic jam up ahead, or are the vehicles moving in a convoy? Good eyesight is a legal requirement for people to drive, but machine learning throws away 20/20 vision before it even starts the engine. Is that really what we want to trust, to drive our children to school in the future, or not to hit us when we cross the road?
It's interesting because convolutional neural networks actually blur the image in multiple ways. And in some respects, that may actually bring out more information than the human eye. For example, there's no reason why it couldn't also use ultraviolet or infrared spectrums of the light spectrum to pull out information and act on those accordingly. So if that were to happen, you could argue that they would be better. That said, of course, it will only get better as it's got enough relevant data. Whilst it's blurring it, the more data it has to work on, the less blurry it will become and the more accurate those models will become. It's also worth noting that these techniques are beginning to overtake or at least parallel humans in their ability. So, for example, there's been recent announcements made on the ability of diagnosing certain cancers based on mammogram images that the AI is actually really, really good at, albeit it still needs a human layer over the top. So whilst data builds up and these things get perfected, it could be that these things actually becomes better, more robust, and in some cases even outperform humans in what they do.
Machine learning being free sounds like a perfect situation for the world. As I mentioned earlier, I worked in an actuarial consultancy for 18 years, and trust me, we did not give away anything for free. No IP, no tools, nothing. But in literally a few minutes, you can download amazing tools from the internet and be coding using pandas or NumPy in Python. Websites are bound to give you help or training when you get stuck. People online will literally jump out of their skins at the opportunity to help you overcome your problems for free. You could even buy a book if you're old school like me. The maths is all hidden, taken care of, and just a few lines of code will fit your super predictive model to your dataset. I've given the random forest code I use to predict my son's sleep duration here to show how superficially simple it all is. There are a myriad of options which are being set to default in that random forest regressor command line, many of which could have a profound impact on the results. And are we sure that when we fit these models for real world use, that we've made those selections correctly? I feel like Jeff Goldblum in Jurassic Park when I ask, is it desirable to enable standing on the shoulders of giants by giving away so much complex power so easily? The range of potential unintended downsides to this situation is huge, even with a well-meaning person at the helm. And what if that person at the helm doesn't have a moral compass like we do? For example, one of the first things I got taught to do on the Udacity Python course, which is a training course used by many companies, was how to send out mass emails using Python. Anyone without a good spam filter knows the impact of that knowledge on the world. And we all have elderly friends or relatives who feel compelled to read and reply to every email out of politeness.
I would argue that yes, there are risks, and we should always be on hand to guard against those. The flip side is I think there is greater benefit to be had by the democratization of data and its applications. The ability to reduce barriers to entry, especially as data becomes more available, would allow us to move quicker, allow more startups to occur, and more generally increase consumer savviness as they're more willing and able to interact with that data, understand what's going on behind the scenes, and likewise optimize their own outputs and outcomes based on the information they receive. I think it's also really important to recognize that we're moving into a slightly different world of how things advance. It's no longer necessarily about individuals advancing it based on trapped knowledge in certain institutions. The ability for people to build quickly upon what others have found and make greater progress more quickly as a community is now available via this open source software. You don't have to solve the same problems that others have already solved. You can get on and solve the new interesting problem and bank that stuff. I'd also just like to face into the issues that most people have around ML, in that this may start removing some of the jobs that we've come to know and love. I actually don't think that's quite correct. I think whilst there will be obviously areas which are disrupted, where there may be jobs that will stop, there'll be many more created, as there's always new problems to solve. And as you find the tools to solve those problems, it's going to be more and more demand for people to help solve those problems using those tools.
Given everything that's been discussed, it's clear to me that machine learning models will bake existing biases into their algorithms, and that these will be almost impossible to detect or to prevent. With classical regression, generalized linear models, you can include a factor, say gender, in your analysis. When you come to produce outputs for real use, you simply ignore the gender input data, take the average value for that factor, and apply it to all genders in your model. And then you will end up with sensible, unbiased output data. Given the complexity of machine learning algorithms, you cannot just feed the model one input variable less and expect to get sensible output data. Think of the neural networks and how they completely amalgamated all the input variables into a new, hidden layer of values actually used for predicting outputs. You can't just remove an input value at the end and expect the model to work. And if you try it the other way, excluding the factor from the start, taking gender out of your model completely, then that algorithm will search like crazy and find proxies for that factor to put the bias straight back into your model. Evidence of this issue regularly features in news stories. For example, I've recently seen stories about the US parole algorithm penalising black prisoners, but there's high error rates in facial recognition software when applied to people who aren't white. As an example, I have a friend who works as a machine learning scientist for Facebook, and when I met him, I excitedly asked him what he'd been doing at work, as I was eager to hear about the cutting-edge analyses he'd been involved in. He simply replied that he and his team had spent the past 3 months just trying to prove to the regulator that the machine learning model they'd built did not introduce bias against protected groups. Not quite as exciting as I'd imagined for him. My perception is that financial services companies are much more heavily regulated than Facebook. So if you work for one, as we do, then do you feel fully able to tell the regulator that the machine learning models you are building aren't biased against any of our customers, particularly those in protected groups? In the UK, the Financial Conduct Authority are flexing their muscles in this area, and we can all imagine the newspaper headlines if someone gets this wrong.
I would argue that algorithms aren't in themselves biased. What makes them biased is the training data or developer introducing that bias, whether it be via the data is biased itself and not selected correctly, or that the developer has overlaid items or assumptions that make it biased. Even if they're unbiased, obviously the outputs can be misused, misunderstood, or miscommunicated, which may lead to biased decisions being made, even if the underlying algorithm or the data isn't biased. What I think we're guilty of looking at is machine learning. Whilst it sounds like it's fully automated, there's absolutely no human interaction, there is still a lot of responsibility on the data scientists, and they are vital to the process. It should not ever be done without a trained, relevant human being have some kind of oversight, in particular around how they validate those models and think it through as to what might go wrong and the input data that's going in particular. We are vital to validating the outputs, making sure that data is appropriate, and of course communicating the limitations of our models so they're not used or misunderstood so as to use them in a way that we are not comfortable with or is the wrong way. It's also worth noting that the algorithms don't have to be machine learning algorithms to become biased or be seen as biased. Recently we had the A-level exam result furore. That wasn't a machine learning algorithm, albeit it was an algorithm. It was a misapplied algorithm, albeit it was using relatively traditional techniques. So these aren't necessarily new problems. However, it does make it more vital, because they're more complex algorithms, that data scientists are appropriately involved and they understand that that is their role as much as anything.
For my final slide, I'd like to talk a little about the unintended consequences of machine learning, the cost to society that entail, and who pays for them. There's a really thought-provoking documentary film called The Social Dilemma, which has a lot of experts in this field expressing their concerns around these unintended consequences. I even saw this film cited by the EU President just the other day for exactly the same reasons which concern me. I think the core issue is that machine learning algorithms seek to optimize what they offer people in terms of news, stories, or videos. The reason being that more likes means more traffic, means more advertising, means more profit for the news media companies using these algorithms. The internet itself is wonderful. It connects people together into communities and interest groups. I can surround myself with people who like board games or tennis or bird watching, whatever. The problems come when machine learning and or the internet create echo chambers around more political issues, leading to tunnel vision and groupthink. The end result of this is a cost to society, which is not borne by the news and media companies benefiting financially from the likes they've created. We can think of this in a similar way to pollution or climate change. Until there is a financial disincentive, then we will continue to see societal harm. And there are numerous examples of such societal harm. Think about headlines in just the last few weeks around the information flows around COVID-19's potential danger, or the risks of vaccinations against it. Think about the information flows around Brexit or US election fraud. I like to think that I try to see both sides of every story. And I've realised over time that these two or more sides almost always exist around every issue, and that nothing is really an open and shut case. Obviously, there are some exceptions, such as who's better out of actuaries and data scientists. The problem is that online we can get insulated from conflicting views, lose perspective, and act in ways that are damaging to ourselves and to society. In this situation, the free market has failed, and governments and regulators need to step in to ensure the costs and benefits are fully considered.
There is no doubt it's true that social media engines are optimized so that based on the likes you've made, they'll select other things for you for your convenience. And they do monetize some of that items as well because they are commercial interests. However, they've also brought great societal benefit. There is no doubting the fact that this range of services and offers that we need to sift through in today's world would be much harder without them helping you, guide you through that using their optimization algorithms. And on the vast majority of topics, that's actually really helpful and beneficial to people. What I would say is it's not clear whether the responsibility here lies with the companies or with individual data scientists and the algorithms. Like most other areas, there may need to be regulation here, and data scientists must work openly and honestly with governments and regulators and the managers of their companies to understand those unintended consequences and help to either innovate to prevent or resolve them via algorithm and or, of course, just make sure that regulations are set out and that the use of people's data is open, honest, clear, such that people can either make informed choices on what they're being shown or that there's certain things that can't be shown. The other thing I would say is echo chambers and the use of information and how they're presented and whether you can get these echo chamber effects has always been an argument. In traditional media, there's always been the case that there are certain papers who cater to certain political audiences and that they too, and that you may have echo chambers form within those silos as well, along with a lot of other things. This isn't necessarily a new problem. This is a wider societal problem which needs to be solved more generally, and that hopefully the data science community can help with. This is an area where Paul and I have discussed a lot. It'd be really interesting to see what everyone else's views on this are. It's clearly a hot topic. Not sure there's a clear answer. It's not immediately clear whether it's up to individual data scientists, their companies, governments, transnational organizations, who should be looking at this and what should be done. But with that, I think we've finished, aren't we, Paul? We're happy to take questions.
We are, yeah. We're very welcome to receive any questions. Or stunned silence, whichever is appropriate.
You'll all need to unmute yourself if you would like to ask a question.
I can ask a question. Oh, no, go ahead, please.
I'd like to ask a question, please. What would you perceive as the best way for someone who wants to get into machine learning, who hasn't done much of it?
So we can only talk about our own past experiences, I guess.
Yes. Yeah.
So there are it depends what you mean by machine learning. If you want to pick up some coding skills that will then allow you to use some of the open source packages that are available. There's plenty of online courses. Paul mentioned one by Udacity, but there are others. We're not advertising just for them, but they're relatively easy to pick up over a couple of months. And then you can start applying the machine learning algorithms. A really good entry point, I've always thought, are the competition sites. I'm sure people have got a number, but the most famous one is, and I can now not remember it, which is really embarrassing. Mine's gone blank. That's it. They're really good because they give you a certain fixed set of data, which is open data. It's nice and clean. You can apply your own solutions and see what others have done in the past. So you can learn how they've done it, what validation steps they've made, how they've fine-tuned, and gradually build up your machine learning skills.
I mean, just to add to that, so it depends what you mean about getting into machine learning. So if you want to get a job in machine learning, I think there's a massive demand for people with Python and machine learning skills. So I think doing some of those courses and demonstrating you can do it to those employers and then applying for a job would be a way in. But if you just want to use it day to day, I think there's so many potential applications. I've mentioned lots of limitations, but there's also lots of exciting applications. So I'm trying to bring this into my day job. So stuff we would have done in Excel or in Glim, how can we think about doing it in a more clever way? And also just automation and better analysis in the same period of time. So I think there's almost a unlimited amount of potential for actuaries to start using these techniques.
Thank you.
I will warn you though, Kaggle's addictive. You'll lose hours, but it's fun.
Kaggle itself has training courses which help you to enter their competition, so they definitely know that once they get you hooked, you'll stick with them.